Calculating the moment of inertia is a bit like calculating the centre of mass. For the centre of mass, you add up all the moments, mi, xi, of all the individual bits of mass and calculate the position about which these moments is zero. For the moment of inertia, you pick your axis of rotation and calculate the moment of inertia mi, xi squared of all the little bits of mass about the axis of rotation. Let's see how this works for this triangle rotated about the y-axis. If we split the triangle into thin little rectangles and work out their individual moments of inertia and then add them all up, this will give us the overall moment of inertia of the triangle about the y-axis. Each rectangular strip is a distance xi from the y-axis. It's got length yi, and it's got width delta x. It's got area yi delta x, and it's got mass equal to its density times the area yi delta x. Further, let's say that the total mass of the triangle is equal to m, and the total area we can see is equal to half times 2 times 3, so it's equal to 3. So that means the density is equal to the mass per unit area, so that's equal to m divided by 3. Okay, now let's work out the moment of inertia of the triangle about the y-axis. We write it as I subscript y, and as we've said, it's equal to the sum of mi xi squared. So we've got some more information that we can put in now. We know what mi is. So the little bit of mass mi is given by rho yi delta x times xi squared. So we want an exact answer, not an approximate answer. So we let the width of all these little rectangles tend to 0. We let delta x tend to 0, and our sum becomes an integral. So we have rho times the integral of x squared y dx. We need an expression for y in terms of x. And we know that our length of our rectangles is bounded by this line that forms the triangle, the hypotenuse of the triangle. And we know that this line is y equals minus 3 over 2 x plus 3. So we just substitute that in. Our integral becomes x squared times minus 3 over 2 x plus 3 dx. The limits are x between 0 and 2. Now we just need to calculate it. So that's rho times minus 3 over 2 x to the power 4 over 4 plus 3 times x cubed over 3 between the limits 2 and 0. So now we just put the numbers in. So that's equal to rho times minus 3 over 2 times 2 to the power 4, which is 16, divided by 4, plus 2 to the power 3, which is 8. And that simplifies to rho times minus 6 plus 8, which is 2 rho. We know that rho is m divided by 3, the total mass divided by 3, so we can write that if we want to, as 2m divided by 3. So that's our moment of inertia. In general, for a triangle with base B and height h, the moment of inertia of an axis, about an axis through the base, IB, is given by rho B h cubed over 12. So what do you think? Can you compare these? Have we done our calculation correctly?